So today we're going to be talking about section 4.4, which is on real zeros of polynomials. Okay, so we can actually continue on with what we talked about in section 4.3, and we can start using dividing polynomials and values that we know are zeros so that we can factor out a polynomial completely, okay, given that we know 1, 0. Now, there's different ways we can be given information that we have a 0, but most of the time they're going to give us one that's known. So let's look at an example. Let's say that we have g of x, and g of x is the function x to the third plus 8x squared plus 11x minus 20, and I know for sure that 1 is a real 0. Okay, I know for sure that is one of my real zeros of my function. So if I want to continue factoring this, if I want to get this down, what I'm going to do is I am going to first start by using synthetic division, right? And since we know 1 is a 0, I'm going to put 1 in the box. And then I'm going to use the coefficients, which would be 1, because remember there's a little 1 in front of x to the third, 8x squared, 11x, and negative 20, okay? And I'm going to drop down the 1, right? I drop it down, 1. Now that's 1 x squared. 1 times 1 is 1, so I add down and I get 9. 9 times 1 is 9. I add down, I get 20. And then you'll notice 1 times 20 is 20, and so I have 0 as a remainder. So we know for sure that 1 is a 0. Granted, they told us that, but it just verifies this. So the polynomial we have left is x squared plus 9x plus 20. And so our job is to figure out what number, like if we think of A, C, and B, right? AC is 20 and B is 9. So what are the two numbers that multiply to 20 and add up to 9? Well, that's 5 and 4. And so when we factor this out, it's going to be x plus 5 and x plus 4, which means my final two real zeros are going to be negative 5 and x equals negative 4. So of the three roots that we have in this in g of x, it's going to be 1 because they gave us that, negative 5 and negative 4 because we found them algebraically. Okay? All right. So let's say then next, they give us a problem right here in example 2 where we're given the zeros and our job is to actually write our function. Okay, so let's look at a problem, and let's say that they give us 3 zeros. They're going to give us x equals 1, x equals 2, and x equals negative 5. And our job is to write what our function is, right? And so we think about this. Remember, everything was always in the term of x minus the root, right? So if you think about it, like back in the last problem, x equaled minus 5, right? And so that's because it was x plus 5, so x minus negative 5. So we're going to think about that when we write this out. So it's going to be x minus the root of 1, x minus the root of 2, and x minus the root of negative 5. So we end up getting plus 5. Now you can do it in any order, but basically what we're going to do is we're going to FOIL, and then we're going to take whatever we get there, and then we're going to distribute to the third one. Okay, so let's do that. So x times x is x squared minus 2x minus 1x, and then plus 2. And all of that times x plus 5, right? And so we get x squared minus 3x plus 2, and now we're going to multiply that by x plus 5, right? And so we say x squared times x is x to the third, x squared times 5 is 5x squared, negative 3 times x is negative 3x squared, negative 3 times 5 is negative 15x, then we get plus 2x, and then we get plus 10. And then we simplify because we can combine some of our like terms in there. And so when I do that, I get x to the third. 5x squared minus 3x squared is going to be plus 2x squared. Then we get negative 15x plus 2 would be negative 13x and then plus 10. And so there's our function right there. If you wanted to verify, what you could do is you could graph this and make sure that it crosses the x-axis at 1, 2, and -5. And I'm assuming it will. Okay? All right. Now, we can also do it where they give us other information. Maybe they give us a 0. Maybe they give us the degree of the polynomial. So then all of a sudden we know what x is. Sometimes they might give us a point. And we can use all that information to compile and create some sort of a function, a polynomial function, using that information. Okay, so let's look at one. All right, so we're looking at a quadratic. Okay, so we remember quadratic. Okay, quadratic. We want it to have zeros of 3 and 9. So x equals 3 and x equals 9 are zeros. And then the last thing we know is that p of 2 equals -14. Okay, so all three of these things are going to help me write some function p of x, right? We know it's p of x because p of 2 is -14. We know that the zeros are going to be 3 and 9. And then we also know that when I put 2 in, I should get -14. Okay, so quadratic is x to the second. So it's nice they give us both zeros. We don't have to find any other ones, right? So we're going to write x minus 3 and x minus 9. Let's FOIL that out and see what we get. So we get x squared. Okay, so that would be x squared. We multiply by 9 would be minus 9x. Then we multiply by -3 would be -3x. And then we take -3 times -9, that's plus 27. And so then I get x squared minus 12x plus 27. All right, so this is p of x, possibly. Okay, I'll put maybe a question mark next to it. Okay, so what we're going to do to verify if there's anything we need to change, we're going to put 2 into the function and see what we get. Okay, so when I put 2 into this, right, I'm going to get, so p of 2 is going to equal, let's see, 2 squared is 4, minus 12 times 2 would be -24. So 4 minus -20 plus 27 is going to be, let's see, 4 minus 24 would be -20. That'd be 7. I want it to be something different. So what do I have to change? Okay, well, something has to change on it. Well, one of the ideas what we can do is we could, because we want to get -14, we said when we put it in, we got 7. Maybe something needs to change that would make it all multiply by -2. So what we could do is just multiply the whole thing by -2 and see what happens, right? So we're going to take back to p of x and we're going to multiply it by -2, multiplying everything by -2, right? Because, and you can think about this, remember, if you think backwards, when we were factoring, right, we would see if there was a greatest common factor that would come out of everything. And then since it was equal to 0 anyway when we were solving, it didn't really matter, right? So what we can do is we can actually multiply everything by -2. And so I'm going to write it over here. So p of x, okay, p of x is going to equal, now, -2x squared. It would be plus 24x, and then it would be minus 54, right? We multiply everything by 2 and then negative. And so what we can do now is we can actually put that value in for x. And so we can check that with the calculator, right? And so we see, okay, so it'd be -2 times 2 squared and plus 24 times 2, and then minus 54, and I get -14. So for sure, that is correct. So we know that this is our value of p of x right here. That's our function. Okay? Cool. Now, rational zero theorem. What is that? Okay? Well, the rational zero theorem basically says that anytime we're trying to find an integer coefficient, okay? Well, excuse me, anytime we have integer coefficients, meaning all of our numbers in front of x squared, x to the third, whatever, are all integers, not fractions, not decimals, but integers, so positive and negative whole numbers. Then, okay, then it can be the case that P over Q, when P is the value or is factors of A0 and Q is factors of AN, we can look at all the possible values of P over Q. So all of the factors of the last number, the constant, divided by all the factors of the first number, right? And the reason that works is because remember when we were looking at, quadratics A, C, and B. A and C, or the values of the first and last number, the leading coefficient and the constant, were important because that's where it helped us find those roots. And that's why it works for all polynomials, in fact. Okay? So let's say that they give us this function right here. They're going to give us h of x. Okay? H of x. And h of x is 6x to the third plus 11x squared minus 3x, and then it's going to be negative 2, okay? So what we're going to do is we're going to look at, first off, we're going to look at all the factors of negative 2. That's P. And then we're going to look at all the factors of 6, because that's Q, right? And so when I do that, okay, the factors of P are going to be positive and negative 1 and positive and negative 2, right? Because 1 times 2 is 2, or whatever. 1 can be positive, 1 can be negative. Now for Q, all the factors of 6 are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are the only factors of 6, which means that, okay, P over Q, here are all my possible rational zeros, okay? So P over Q looks like this. And I'm just going to use plus or minus the whole time. All right, so P over Q. So it could be 1 over 1, which is 1, right? Then it could be 1 over 2, which is 1/2. Okay, could be 1 over 3, which is 1/3, or it could be 1 over 6, which is 1/6. Okay, then I can do 2 over 1, which is 2. 2 over 2 is 1, which we already have. 2 over 3 we don't have. And then 2 over 6 is 1/3, which we do have. So these are all, it wants us to list all the possible rational zeros. Here they are right here. Okay, so you have a total of 1, 2, 3, 4, 5, 6, and then positive and negative. So there's actually 12 different possible rational zeros. It's not all zeros, but that's the rational ones that it could be. Okay. All right. Very good. Okay. Now, finally, we're asked to find all the zeros of a polynomial function. Okay, so we've looked at when they give us a zero. We've looked at ways to figure out what one of the zeros are. We figured out if we have the roots, how to write the equation. Here it is now. If they just give us a problem, and we're actually asked to find all of the roots, right? This is the essence of algebra. We're asked to find the unknowns for a value. Okay. All right. So let's look at one right here. All right, and we're going to look at. Let's see. Here. And we're going to look at a function f of x, right? So here's f of x, and it's 2x to the fourth minus 21x to the third plus 78x squared minus 119x, and then finally plus 60, okay? So we're asked to find all the possible values that this could be. Now, thinking about it, we have 60, so all the factors of 60 are going to be, there's a whole bunch of them. I guess we don't even have to name them. And then right here we have factors of 2. And so there's a whole bunch of them that we could possibly have. And so we kind of think of, well, what's a starting point? Well, what are some of the factors that might work? Okay, well, easily enough, we can see that we can't take a 2 out of everything, so we can't factor it out. But we can just start with a couple different numbers. Okay, maybe an easy one to start with, for sure, 5 is an option, right? Because 10 is a factor of 60 divided by 2, right? So 10 divided by 2 is 5. So let's try 5, right? So we're going to put 5 in the box, okay? And so 2, negative 21, 78, negative 119, and positive 60. Let's see what happens, right? So we drop down the 2. 5 times 2 is 10. We get negative 11 times 5 is negative 55. Okay, we add down, that's going to be what, 23. Multiplied by 5 is going to be 115. Okay, add down, we get 4. 5 times 4 is 20, and so we add down, I get 80. Okay, so that doesn't work, right? What if we tried negative 5? Because we can always do that, right? So this would be negative 10. So now our numbers are going to change just a little bit, right? Our numbers are going to change. So let's get rid of these, okay? These numbers are going to change, right? And we're hoping that we get a 0, right? All right, so that would be negative 10. We add down, we get negative 31 times negative 5 is going to be a positive 155. Okay, it's a big adding problem. So 3, carry the 1, we get 3, carry the 1, you get 233 times negative 5. It's going to be some huge thousand number, right? So we can stop there because we know that that's not going to work. Okay, so all right, so we give up on that. Okay, we give up on 5 and negative 5. All right, so let's try another number then. Okay, so we could think of some other factors, right? And we'd get 2, negative 21, 78. Okay, so let's try a different number instead of 5 or negative 5. Let's try maybe something bigger. Maybe let's try, 5 was pretty close, so let's try 6. Okay, it was pretty close we had 20 or 80 left over. Let's try 6. So we drop it down and we get 2. So 6 times 2 is 12. Okay, I add down, I get negative 9. Okay, here I'm getting negative 54. And so that would be 24. 6 times 24 is going to be 100 and, let's see, 24 and 120, 144, right? And so then when I add down, well, I'm going to get something that's going to be positive, and then this is going to be, it's going to be something, let's see, what's this? 25 times 6 is going to be 150, and so then we get too big. Okay, so we're going the wrong way, and that's all right, no big deal, but it gives us a little bit of a hint, right? If we're going up when I add numbers, right, when I go from 5 and 6, right, let's think of something that's smaller than it. Maybe let's try 4. Do you think 4 is a factor? Well, if I think about it, 4 is a factor of 60, right? For sure it is. So let's take 4 and let's try it here. Okay, so 4. So drop down the 2. Okay, then I get 8. Okay, so then that's going to be negative 13 times 4 is going to be 51, right? No, excuse me, not 51. 40 and 12 would be 52. So this is negative 52. Okay, so I get 6, 26 times 4, 80, 104. Okay, so when I add that, I get negative 15. Hey, check it out. Negative 15 times 4 is negative 60. So now we get 0. So now we know for sure that 4 is one of my roots. And the cool thing is now I have this left over, right? So, okay, so I have 0 here. So now I'm going to cross out that 0. And I know that 4 is one of my roots. So now I have to think of another root of what's left here, okay? So I know 5 and 4 didn't work. It's probably not going to be anything too big. So maybe let's think of some other factors of 60 and 2. Maybe let's try, well, 7 isn't going to work. Is 8 going to work? Let's see, factor 8 doesn't go into 16, doesn't go into that, no. Maybe, how about we try something easy? How about 3? All right, let's see if 3 works. All right, so drop my 2 down, right? And so 3 times 2 is 6, get negative 7, times that would be negative 21. And so then I get 5 times 15, and I get 0. Hey, check it out. That's good, okay? So now I have 2 of my roots, right? That's pretty awesome. I have 2 of my roots. It's 4 and 3. And so now I have a quadratic, and those are way easier to solve. So AC in this case would be 10 because 2 times 5 is 10, and B is going to be -7. And so the two numbers that multiply to +10 and add up to -7 are going to be -2 and -5, right? And so what I can do then is I'm going to write, so it's going to be 2x squared minus 2x minus 5x um, plus 5, right? And so I factor by grouping, and I take a 2x out of here. Um, Actually, I'll write it down here, actually, so we don't get confused. Okay, so I get a 2x out of here, and then I get x minus 1, and then I take a -5 out, and I get x minus 1, which means that my final two roots are going to be 2x minus 5, and I'm going to get x minus 1. So my final solution here is my 4 roots, because it was x to the 4th, so it's probably going to have 4 roots, maybe multiplicity, but probably not. We get x equals 4, right? X equals 4, that was the first one we found. X equals 3. Then here we could see that x equals 1, so we could have used 1 from the beginning. That would have been nice. And then the last one's a little bit difficult. That one's actually going to be 5/2, which we wouldn't intuitively think to try, but it ends up working. So there are 4 roots right there. From start to finish, that's what we got. Okay? Very good. All right. Now, the next thing we're talking about is Descartes' rule. Now, Descartes was a French mathematician, and he found that if you look at the sign changes in any root or any polynomial function, the number of sign changes when you put in an x, right, or positive x, the number of sign changes would be the number, okay, would be a possible number of or excuse me, would be the possible number of positive real roots, right? And if you put in a negative x, okay, you could find the negative number of real roots, and anything else would be unknown, or since we know the future, it's going to be imaginary numbers, right? And so we can look at any polynomial function, we keep x. The thing we remember is that even roots or even powers are going to remain the same, be positive, basically, because a negative an even number of times is going to be positive, and then odd roots change the symbol if it's negative. So that's what we can do. Okay, so let's use Descartes' rule. Let's look at a problem. Let's use Descartes' rule to try and figure out actually how many possible roots something might have. Okay, so I'm going to look at p of x here. P of x is 7x to the 4th minus 2x to the 3rd plus 8x squared minus 11x and then plus 6, okay? And so I'm going to try and figure out the number of positive real roots, okay? So if I'm trying to figure out the number of positive, okay, we look at sign changes. So here, that's one sign change. Negative to positive, that's another sign change. Positive to negative, that's another sign change. Okay, so we can possibly have 4 positive real roots, okay? So, so 4 positive roots, okay? Up to have 4 positive roots. Now, let's look at p of negative x, okay? And so that's like saying p of negative x to the 4th, then minus 2x to the negative x to the 3rd, and then we get plus 8 negative x squared, and then minus 11 times negative x, and then plus 6, okay? So that reduces to, okay, reminding ourselves that every time there's a positive root, changes it. So this is going to be, or make it positive, so 7x to the 4th. Now negative x to the 3rd would be negative x, so times negative 2 would be 2x to the 3rd. Negative x squared would be x squared, so it would be plus 8x squared. Then right here we have negative 11 times negative x would be plus 11x and then plus 6. And notice as I go across, I don't have any sign changes. So there's going to be 0 negative roots. Oop, I wrote negative. 0 negative roots, which is interesting because now that helps us know if we think about, I still wrote again. If we're thinking about all of those rational roots that we could have, the pluses and minuses, now we know for sure we don't have to worry about any negative numbers. We can just look at positive ones. So that's kind of helpful, okay? And it's going to be really helpful in the next section when we talk about imaginary numbers. All right, and finally, the last thing we're going to talk about is upper and lower bounds. And so basically, we can determine where all of our roots are between, upper bound being the biggest value or bigger than the biggest value of our roots, and our lower bound being smaller than the smallest of our negative roots or zeros or whatever. And so basically, what we can do is they can give us some values to determine if we have upper and lower bounds, okay? And so what we can do is we can determine whether each one does that. Now, the way we do that is by looking at an example. We're going to look at a problem where they give us the function x to the fourth plus 14x to the third, and then we have plus 56x squared plus 34x and minus 105. Okay, so here's a function that is f of x, all right? And they tell us that our upper bound is 2. So upper bound is 2, which means all my roots should be less than 2. And my lower bound is negative 15. Okay, negative 15. And so so I want to verify this by doing some synthetic division. Okay, so and there's a couple different rules, and so you want to make note of those. Okay, so our upper bound is 2. So I put all of my coefficients in. So 1, 14, 56, 34, and then negative 105. Okay, and so I drop my number down. Oops, excuse me. Drop down a 1 out of 2. Drop down the 1, so I get 1. That would be 2. Add down would be 16, 32. So now I'm at 88. Okay, multiply by 2 is 176. Add down, it's going to be 210. Times 2 would be 420. And I get 315. Now, what do you notice about all of these numbers right here? Okay, all of those numbers right there end up being positive, right? So because there's no negative numbers on the bottom, okay, no negatives, we know that for sure 2 would be an upper bound. Okay, so no negatives mean it's an upper bound. Upper bound. Okay, that's good to know. Okay. Now, let's use the same information, okay, and do a little subtracting here. Okay, we're going to use the same information, and we're going to look at what happens when we put negative 15, and we're going to look at to see what those numbers are and what our rule is then, okay? All right, so I'm going to put in negative 15. Okay, so I drop the 1 down. That would be negative 15. I get negative 1. I get 15, and I'm going to get 671. Multiplied by negative 15 is going to be negative 1,065. So I get a negative 1,031. Multiply that by negative 15. This is a big number, 15,465. And then I add down and I get 15,360. Now, what do you notice about all of these numbers, right? Positive, negative, positive, negative, positive. Now, because they alternate signs, we know that it's the lower bound. So if it didn't alternate signs, right? If it was positive, positive, negative, positive, negative, it wouldn't be considered a lower bound. So that's just helpful information. You could use this information if you had all of those rational values like we did, and then you figured out how many positive or negative real roots there are. and then you put them in, put in some positive ones, and you see that they're all positive, right? If they're all positive, then you know that, oh, this is too big for all of them, so we can go smaller, right? Or if you see that it's possibly, you put in a positive one and they're all alternating like this one, oh, that's too low. So now I'm starting to simplify to get down to it and kind of pigeonhole ourselves into something, okay? All right, well, hopefully this was helpful. And if you have any questions, comments, concerns, please let me know.